Applied Physics COLLOQUIUM, and we are so happy to begin to have COLLOQUIUM in person. Today we have our very own Hwang to give the talk of the discovery he made. Today also is the first time we also try to do hybrid with people in the audience and also people over Zoom. So Harold started his career at Bell Laboratory, the telephone company, which discovered so many things impact our life. Then he made a detour to Tokyo, and 10 years ago we are so fortunate to be able to attract him to come here to Stanford, and he's been here since then. He's been a wonderful departmental citizen, been doing all sorts of things, and leading research, and he's also now the head of the material science division at SLAC. Harold has a joint appointment between campus and SLAC, and also the director of the Institute for Material and Energy Sciences. Harold has many awards. I'm going to read a few of them. He got, I believe, it's the very first Materials Research Society Outstanding Young Investigator Award, the IBM Japan Prize, Fellow American Physical Society, the Hwang Prize, and the Euro Physics Prize. His research is in condensed matter physics and material science, correlating electron systems and emerging phenomena at artificial interfaces. That's where he has a signature work. Atomic scale synthesis of heterostructures of quantum materials, oxide heterostructures for energy applications, low temperature, low dimensional superconductivity and devices for interface states. For someone in the field, I think the signature about Harold's work would sort of define him really remarkable and unexpected discoveries. I think when he was a graduate student, that was the famous paper together with Takagi and others on this linear resistance in the normal state of the cuprates persists up to 1,000 Kelvin. That's one of the real signatures papers. Then he also discovered remarkable spin polarization in the manganites that leads to that field, exciting field in the manganites. He stunned the community by discovering high mobility at the interface of two oxides, LTO and STO. That's a field, for those of us that work on materials, sort of impossible to create such a clean interface with high mobility. He made it happen. After he came to Stanford, he made the discovery of remarkable broadband PM junction detectors using black phosphorus. And 2 years ago by now, he stunned the community again with the discovery he's going to discover today. Harold.
All right, thank you, ZX. You're going to be let down after that intro, but that's okay. Very pleased to... Speaking off the moon, am I doing something weird? Or is this all good?
We can hear you.
All right, good. Anyway. It's weird and strange and wonderful to speak to you in person. I haven't done this for 2 years, so I'm not sure what I'm doing, but let's see how it goes. So yeah, thanks again for this opportunity and all your time. Great to see you together. So I'll tell you the story about some of the work we've been doing in this layered nickelate system. And I was asked in the context of this audience to try to give some broad introductory kind of start relevant for students across disciplines in physics. And so, I was thinking about that, and in some sense, one of the important things what I could do is to introduce that this was very much Ted Jabal's field. As you know, we said farewell to Ted, our colleague and mentor, a week ago. And so somehow I couldn't avoid thinking about that when I was thinking about our introduction.
So it was a moment of sadness, but also a great celebration. For those of you who don't know, he passed away at 101 years old and 9 months, and had an incredible career, one aspect of which is the field of discovering and developing new superconducting materials. Just as a personal anecdote, in 1990, I was a summer student after my sophomore year in college at Bell Labs in Murray Hill, New Jersey. And I walked into my first day assignment in this room. Some of you may recognize the number, which was Joe Ramika's old lab. And I opened the door and I looked up and there were these three distinguished gentlemen in this picture. And I didn't know who they were. Every day I went to my office and there was this picture. And eventually, also for those of you who know, my mentor there in using this lab was Song Chung as a postdoc at Bell Labs at the time. So he told me a little bit of the story, and I remember thinking, crikey, physics is hard enough. You got to be smart, but you apparently have to be really good looking as well, right? So that was intimidating. And Ted obviously seemed to like to work in trios. And as you know, he was here for many decades as a founding member of the department, forming this famous KGB group. Right? And so, anecdotally, it turns out that I roughly followed his footsteps approximately 40 years after when he went to Bell and after he came to Stanford. And so think about the work we're discussing today is very much in this field of superconducting materials. Let me see, maybe I'll use this one. All right, cool. Okay, so what can I tell you a little bit about superconductivity? It's a very vast field. It has some interesting origins that very much jive with my own kind of tinkering and sense of laboratory work. The starting point, I seem to have lost all control. Yeah, the starting point was in the group of Carl Magnonis. He had a research group at Leiden University, and one of the things they specialized in was liquefying lower and lower boiling temperature liquids. And in 1908, they got to liquefying helium in bulk quantities, and it gave them kind of a monopoly of exploring the low temperature limit of metals, right? And in 1911, these guys discovered superconductivity in mercury. And here's a trace from his lab book then. It's a nice thing that the TC of mercury is around 4.2 Kelvin, which is the boiling point of helium in ambient. Right? So the context is really remarkable if you think about things in proximity in physics, right? This was not so long after the discovery of the electron, about a decade after this phenomenological Drude model of conductivity, not knowing the microscopics, but thinking that I have charge carriers of some density, fundamental charge, and that I could think of this as some sort of relaxation time type of picture. And the bottom line is this is far before there was a quantum theory of solids. And this to me is kind of interesting because at that time there were a lot of basic questions, right? So there's some phenomenological scattering time. Metals tend to get more and more conducting at low temperatures. There are big debates about what happens in the zero temperature limit. Maybe all the electrons just freeze and you become an insulator. Or maybe you go all the way to being a perfect conductor. And rather what they found was this peculiar transition, right? It turns out that they first studied platinum and found that platinum saturated with the residual resistivity. And one of the features of mercury is that it's a liquid metal at room temperature, so they could play around with distilling it and various aspects of their properties. So since that discovery, many, many things had to be understood, both theoretically and experimentally. So that's what these three dots stand for. But again, to give you a very terse survey, one of the important experimental aspects that led to a microscopic understanding was that in many superconductors, if you could change the isotope of the elements, found this relationship that the square root of that mass times Tc is often roughly a constant. It turns out Ted found one of the first exceptions of that in ruthenium, But this picture led to the simple association that if I remind you of a harmonic oscillator, a mass on a spring, the resonant frequency goes the square root of the spring constant over that mass. And this square root of this ratio also sets a scale, for example, in a ball and spring model for the sound velocity in terms of the acoustic branch of phonons. So this was one of the key experiments that led to the thinking that phonons and electron-phonon coupling must be intimately related to superconductivity. And so subsequent development of various pictures led to the following understanding that if I have in second order in the electron-phonon coupling, I can have a virtual interaction between two electrons that is net attractive. And a qualitative picture might be something like this. Okay. At this point, thinking about superconductivity in metals, I have a fast electron with a fast Fermi velocity zipping through, and there's a delayed reaction in response of the lattice. And this delayed reaction can mediate a net effective interaction between the electrons as a second electron gets attracted to this lattice distortion. Okay. So this kind of a picture can lead to the finding that if I take two electrons, I can bind them with equal and opposite spin and momentum into so-called Cooper pairs and gain energy, or condensation energy with this. And if I can come up with a way to make a macroscopic quantum coherent state using these Cooper pairs, what followed was the development eventually of a microscopic theory of superconductivity using this electron-phonon mechanism. Preceded by almost a decade first by an effective phenomenological theory taking this notion that you have this macroscopic quantum wave function. So a very terse summary, but kind of a sketch of the starting points of the field. And starting around that time, a little bit before, interesting and useful superconductors were found. So again, just to give you a few examples. So in 1953, the first of the A15 Chevreul superconductors was found, B3SI. And a year later, Ted and Bernd discovered niobium-3 tin. And so for those of you, I don't know, for some of the students, if you use high magnetic fields, let's say above, 11, 12 Tesla in your lab, that's what's in your superconducting magnet. If you've ever had a medical MRI, that's again, thanks to TED, right? So other peculiarities, dilute semiconducting superconductors, heavy fermions, and of course a big shock to the community was in the cuprates. And so a lot of these later examples were increasingly pointing to the notion that it doesn't seem like this conventional picture of electron-phonon coupling is the right kind of starting point in thinking about pairing in these systems. And certainly the cuprates were a fairly extreme example of that. I think I'm also perhaps too young to really sense the shock it must have been. This is kind of a messy, brittle oxide ceramic system. It's not even a good metal, not to mention why should it be a superconductor. In fact, it manifests these electronic correlations that are poorly screened in the fact that if you look at the so-called parent compound, lanthanum 2-copper-04, if you thought about the electronic structure in the conventional ways, you would conclude that this was a metal, a half-filled band. But what it turns out is that the electron-electron interactions are so strong that rather than a metal, the electron kinetic degrees of freedom are frozen and charges localized on each side, such that all that's left is the spin degree of freedom and the ground state is an antiferromagnetic insulator. And so what Bednorz and Mueller found was that if you did substitutional doping, a little bit like phosphorus doping in silicon, by putting barium 2+ and lanthanum 3+ site, that you could whole dope the system and find superconductivity, right? At fairly high temperatures, and namely temperatures that are too high to understand via this electron-phonon picture that I previously showed you. So I didn't actually go back and check that this is true, but I could imagine that every year in this colloquium series, at least 1 or 2 talks must have been on the cuprates, right? So it's been an enduring problem and remains so to this day. It's very complex. This is a recent review article, shows you some of the basic features. You have this antiferromagnetic insulator, and upon doping, a dome of superconductivity. And I won't try to go through all of this, but lots of other strange features, both in terms of the normal state before you go superconducting, all sorts of competing stripe or density wave instabilities and so forth. Right? And so I certainly don't believe, first of all, there's much more expertise in the audience, and I don't believe there's a current consensus on this problem. The degrees of freedom that are clear are that the electron correlations are in a fundamentally different strong regime. And questions arise about how those interaction effects may manifest different channels of pairing, such as via spin fluctuations, via stripe instabilities, maybe bootstrapping off of electron-phonon coupling. It's a very strongly coupled problem. In terms of the materials, there are probably hundreds of different cuprates nowadays known. They all share a common structural motif, by and large, of being composed of CuO2 planes. So it's a quasi-two-dimensional crystal structure with different sequences of stacking of these planes, right, in their proximity and different interspacing layers. So one of the quotes that I like is if any of you are fans of Michael Lewis, his first book was Liar's Poker, and he was quoting a fellow banker, actually, in that context. God gave you eyes, plagiarize, right? So with a slightly, hopefully more positive notion, that was certainly a lot of the thinking driving investigation of other complex oxides. So given this unexpected discovery, thinking, what other systems may share fundamental degrees of freedom related to the cuprates? And can one find other superconducting systems in this vein? So quite soon after this launched extended investigations of other layered nickelates and other transition metal oxides. The 3 that are kind of closest to the types of things I'm going to be talking about is the same 214 nickelates with rather than 9, 8 d electrons. A family of square planar nickelates. This is what I'll tell you about. Our work fits in this vein, if you will. And other recent examples where people have been thinking about engineering the electronic structure in superlattices. So that's the agenda. I'll try to tell you about this work, both from ours and other groups recently. It's been an exciting time. In order to do that, I first have to acknowledge quite a long list of people. This is only a partial list of people within our own group over the recent years, local collaborators here at Stanford, strong collaborations on electron microscopy and spectroscopy with a group at Cornell. As you'll see, we're very dependent on close collaborations with X-ray scattering and spectroscopy given the sample geometry limitations that we have. Theory, and somehow we haven't collaborated, but I ask you for advice here and there. So Steve, I acknowledge you. So what is the basic idea or question in this framework? Which is, can you make layered nickelates to have the same layered crystallographic structure and electronic structure as found in the cuprates? And so I just gave this direct analogy to the so-called infinite layer cuprate, which is the antiferromagnetic insulating parent compound of cuprate superconductivity. So here's my periodic table, or part of it, and nickel is next to copper, so you may think that if I can make nickel 1+, it might fit and look like copper 2+. And indeed, that is the case. If I can make such a compound, I could have this planar configuration with nominally 9 d electrons, namely leaving an unpaired electron in the uppermost dx squared minus y squared orbital. And I believe there were people thinking about this even before this, but at least 2 early theoretical or computational considerations I show you here from 1999 and 2004, both thinking about this possible analogy and the potential of these sorts of materials to host similar types of superconducting instabilities, and a subsequent paper that suggested there are actually important qualitative distinctions. And so this is a density functional calculation from this paper in the uncorrelated limit. And what they find is that there's big hole-like Fermi surface, and this looks very much like that of the cuprate problem, coming from this orbital hybridizing with the oxygen 2p states. But that in addition, there was this other different feature, these little electron pockets. There's one in the zone center here, which is derived from hybridization between the lanthanide 5D state and the nickel 3D state. So this is a little bit different. And the notion is that this is a bit of a self-dope system. I have this kind of two-band picture, and in different cases that might be very germane for the experiments that I'll describe to you. Now for those of you with more of a materials or chemistry orientation, you'll immediately say, hey, this is very, very strange, right? Monovalent nickel is not something that, that is common or should be thermodynamically stable, and indeed it doesn't seem to be the case. This is a chemistry-oriented periodic table, so here's kind of the principal oxidation states. So nickel likes to be 2+, like nickel oxide. At high oxygen pressures, it can go to a 3+ state, and we want to make something really extreme and different from that. So how is this possible? So we're really relying on very creative chemistries that have been developed over the last few decades. And I'll just illustrate to you the way this works. The first experiments were done by taking powders of the perovskite form of nickelate. So this is a 3D perovskite oxide. Here's the crystal structure with nickel anomaly in the 3+ state. So you have to synthesize this at high pressure. And by flowing hydrogen gas at relatively low pressures, they suggested there was a sequence of reduction or topotactic reduction reactions where essentially you pull out a row here and here and here and here of oxygen to make an intermediate phase that has one more d electron, one less oxidation state. And if you go further and pull out the other row of oxygen, you get this infinite layer structure. And at some point at the end, I'll explain this terminology, hopefully. So this small subfield was actually quite controversial. There was big problems reproducing this, and an important step was this group that showed that you could use metal hydrides to very reliably do this reduction chemistry. And for the work that I'm going to show you that we built on, also a key development in 2009 from two groups in Japan that found that you could do the same kind of reduction chemistries in thin films. And there's some advantages to doing that in thin film form that I'll tell you about. So just to give you an idea how this looks like, so this is a picture of one of the growth chambers in our lab. We're using a specific version of physical vapor deposition, and a number of us here at Stanford have been interested in this technique as a way to grow with increasingly clear atomic precision, rather complex heterostructures using these sorts of perovskite oxides. So Yuri Suzuki, Will Choi, and Matt Tsai. There must be others as well. So this is a rather, let's say, expensive and elaborate technique, and this is how we're growing thin films. This is actually another perovskite, so this is how it looks like by electron microscopy. This is a 4 angstrom building block, and this is the way we grow our starting thin films. And then the key additional step looks very simple and primitive. It actually is. So for this deintercalation reaction, this is a small piece of our film, loosely wrapped in aluminum foil, and these pebbles are calcium hydride. So we're vacuum sealing this in glass tubes to pull out these planes of oxygen, so-called apical oxygen in the cuprate context, to form this metastable phase that we're going to study. So really, probably the most important thing that we had been doing on this problem is trying to understand this rather challenging materials chemistry problem. As I already told you, nickel has these preferred oxidation states, and we want to do something rather peculiar, actually. Right? What we're trying to do is to hole dope the system. So we hole dope the perovskite phase by chemical substitution to a very extremely high oxidation state and then reduce it to a very low oxidation state. We're trying to do this in thin films to use epitaxy to stabilize our structure, but all the while as we go from this phase to this phase, the lattice constant expands by about 3%. So it's a really kind of a catch-22 kind of problem that's been quite fun, but certainly challenging to work on. And the first hints of anything interesting well, anyway, here's the date. What you see here is the resistance as a function of temperature of a partial transition. You can see that we're far from zero here. It gave us a first taste of something interesting might be going on. Okay? So it took us a good part of a year to get to the point where we thought we knew what we were doing and to submit a first paper on this. And this is kind of a snapshot of what happened in between. It turns out that this partial transition was just due to this tiny sliver of material you can barely see right up against the interface. And the bulk volume of the film, the rest of this is all a mess. It's decomposition, second phase products. You're not supposed to understand more than this looks terrible, and indeed that was the case. And so we spent quite a bit of energy trying to grow and stabilize this interface phase. And kind of the final qualitative step or realization was that the substrate, in this case strontium titanate, which doesn't undergo this reduction chemistry, gives you a very nice proximity effect. It kind of templates over a few nanometers the orientation of this layered nickelate structure. So the final step for us was to think about making a heterostructure to cap this tri-layer with the same material such that we can orientationally stabilize this from both directions. And so what that allows us then is to get to single crystal thin films up to 10 to 15 nanometers. Hey Bob, what's up?
Growing the strontium titanate, the second, there's epitaxy growing it?
Yeah, but just to be clear, we're growing this on top in the perovskite form. So at that point, this is nickel 03. So we're growing all, this is our substrate. This is a thin film at that point of perovskite nickelate. And then on top of that, we grow strontium titanate. Then we reduce everything, but that reduction occurs just in the nickelate layer. I'm only showing you the consequence.
Okay, so the strain that you're constraining with the strontium titanate is all lateral.
It's all lateral.
Strain. There's nothing going
There's nothing going on vertically. Yeah. So that's a good point, actually, that I won't go into the details, but everything I'm telling you about, since we're in this thin film regime, the in-plane lattice constants are artificially constrained to the substrate. So it is not, let's say, the natural lattice constants of that system. So that might be important, actually. In any case, with this kind of sequence of materials developments, we could get to a regime where we had, I'll go back into the details in a moment. You see extended defects here, so it's not perfect, but a single phase film where we could reliably understand that that's what's going superconducting, and I can tell you a little bit about the properties. So at that first stage, you know, why did we land on 20% strontium? Well, we just said, well, if it's going to be like a cuprate, maybe that's where the dome is. And so this was just a flyer, let's say. I'll show you the doping dependence in a moment. So let's look at that perovskite form. So this is what we grew in our growth chamber, the perovskite form of the nickelate. And as we just discussed, capped with strontium titanate. This is a famous system for those in our community in that neodymium nickelate, for example, goes from a paramagnetic metal through a strong first order metal insider transition associated with spin or orbital ordering. Okay? And if you hole dope the system, it turns out you suppress this metal insider transition and you have something that looks nominally metallic all the way down. So if you take these starting materials and pull out one of the oxygen or planes of oxygen to get to now O2 phases, if we look at the undoped parent compound, we see something a little bit strange. It's not really a good metal or an insulator. We have a weak, roughly logarithmic upturn. But for the case that we've now chemically hole doped this, nominally at the 20% level, indeed this thing looks superconducting. Right? In fact, if I don't label this, this doesn't look so far even in the resistivity scale from a cuprate. So if we look at the early superconducting properties of this system, it exhibits a critical current density at that point of about 0.2 megaamps per centimeter squared. Recently, that's gone up by about an order of magnitude as samples get better and better. We can put on a perpendicular magnetic field to suppress superconductivity and therefore estimate the superconducting coherence length. That turns out to be typically 3 or 4 nanometers in scale. And finally, in terms of, this is a bit strange, right? Nowadays it's pretty common, but in the old days, when I was a student, it was very, a requirement for reporting superconductivity is Meissner effects, thermodynamics, or something. I guess in the 2D world, we get a little bit of a latitude. But one of the ways we tried to probe some aspects related to this was using mutual inductance. That is to say, we put our thin film sample between 2 coils. We drive an AC magnetic field with 1 coil, and then see what gets through in a pickup coil, and you can see the onset of screening at the superconducting transition. We're still actively studying this, so there are lots of details we don't fully understand, but just to give you a scale, the London penetration depth that we infer is of order microns. So it's rather long, actually, implying a rather low superfluid density. And the final basic story I can tell you about the superconducting properties, slightly different compound, but don't worry about that, is looking at the resistive upper critical field. You don't need to worry about all the details here, and this is basically just to say that if you look at suppressing superconductivity by a perpendicular magnetic field, so perpendicular to the plane, or in the plane direction, parallel, what's surprising is that the HC2, the upper critical field, is basically isotropic. We don't know of any other layered oxide superconductors that have that. Usually it reflects the anisotropy of the electronic and crystal structure. A second aspect that is quite puzzling is that most of this upper critical field seems to be Pauli-limited. That is to say that the suppression of superconductivity can be coming from the pairs running around, so orbital depairing, but rather it seems to be set on the scale of the Zeeman, right? That I flip one of the, or the anti-parallel spin configuration of a Cooper pair. So in some sense, this is great. We were lucky or fortunate or whatever, and we found this new superconductor, and certainly in the framing logic of going after this, a comparison with the cuprates has guided a lot of our community's thinking. And a starting point is just to ask, well, maybe this is exactly what you had hoped for, right? That 9D electrons, whether it's on a nickel or a copper, is basically the same. And is that the case? So this is kind of the types of things that we've been thinking about. And so indeed, the starting point has some qualitatively similar, but also distinct features that I'll describe to you. So here's a schematic of the Cuprate landscape. So I have density of states associated with, say, oxygen 2p-like states. And again, this dx squared minus y squared orbital state that is split by a strong Coulomb interaction, right, to a so-called lower and upper Hubbard band. So when you hole dope the system, an early idea was the notion that you have a strong Zhang-Rice singlet formation is a nice picture. Namely that because of this alignment, especially this oxygen 2p band, that the nature of the holes is actually not purely copper-like, but really resides in this oxygen ligand field. Right? And so this gives you both an overall singlet and a nice, interesting kind of connection to antiferromagnetism and their fluctuations in this square planar lattice. Okay, so in the nickelate case, we have a similar but shifted landscape. So by analogy, then we have our upper and lower Hubbard bands of the nickel, dx squared minus y squared levels, but it's quite a bit higher than the oxygen 2p band. And so this is interesting in 2 regards. One is by hybridization, we still have something that looks like this. This is a Wannier projection of that kind of band. This is kind of the big hole-like Fermi surface in Warren Pickett's calculation I showed earlier. But in addition, that because you have this hybridization between nickel 3D and, say, in this case, lanthanum 5D, or the lanthanide 5D state, you have something else that is much more three-dimensional, right? And so this is that electron pocket, if you will. Right? And so this is kind of an interesting configuration that is quite distinct from what you find in this picture. Yeah.
I'm not sure what the picture is showing.
So
This is real, no, the 2D and 3D, this is a picture in real space of the Wannier function? Or?
yeah, well, actually half the authors are in the audience. So this is a Wannier projection of essentially this guy. Oh, shoot. Let's say the electron pocket version, and then the whole Fermi surface.
Uh-huh.
Yeah. Are we cool?
What are all the colors?
What are all the colors? That's beyond my pay grade. I presume that this is, for example, well, I don't know. Hey, what are the colors?
Pluses and minuses.
These are basically the lobes. Like this would be like a oxygen. It's just the sign of the lobe, no?
I see.
Right. So this thing would be like the pluses. I don't know which one's which, but the pluses on the copper dx squared, and this is the minus, and so forth. Don't jump up to rescue me, guys. Well, last time I talked about this, I got beat up by this man about what a singlet is. So hopefully...
Don't worry, we don't do that.
Sure, Bob. So some of the things that kind of spectroscopically give the backbones of this picture, I'll show you here, for example, the oxygen K edge. So X-ray in and looking at the absorption associated with these transitions. So looking at, say, nickel 2+, the perovskite nickel 3+, or the infinite layer phase. In these two earlier cases, you see this strong hybridization P peak associated with that guy as a feature preceding the oxygen K edge. But both in lanthanum nickel O2 and neodymium nickel O2, this is vanishingly small in the case of the D9 electron configuration. And so this is by X-rays. By electron energy loss spectra, you have access to rather similar features, effectively. And so this is looking at the oxygen K edge regime laterally through a cross-sectional TEM sample. And again, the same story, that in the perovskite phase, you have this pre-peak that is absent in the planar nickelate. And so at the nominal level, the conclusion of these sorts of studies is that we're in the so-called Mott-Hubbard regime, which is a little bit weird for this side of the periodic table, but again, we have this very low oxidation state for nickel. Another important question is, what is the nature of holes in this compound when we substituted strontium, right? And so, for example, in the 214 nickelates, it turns out to be in the high spin state. And for example, a number of people, here's some early guys worrying about whether or not you're close to this high spin and low spin transition. And for those of you not familiar with the details, the idea is very simple, which is that we started out with these 9d electrons. If we hole dope or pull one of them out, you may think that we're just going to pull out this top electron, but actually it's possible that you'd rather pull out this lower electron. And the reason is that you have this strong on-site Hund's rule coupling, right, to minimize kind of exchange effects. So it's kind of a function of the level splitting versus this coupling, which wins. And to make a long story short, by looking at the X-ray absorption spectra on the nickel L edge, the story seems to be consistent with the low spin state. Okay? So let me tell you then about a little bit about the phase diagram. So this is a doping-dependent study. Wow, somehow I'm going slowly. Let me try to go a little bit faster. And I'm comparing this with this 2,1,4 cuprate. And one of my many mentors in this field, Hide Takagi, had done this work quite a long time ago for the 2,1,4 cuprates. So what we find is a similar superconducting dome in terms of the rough features and the doping levels. An interesting distinction that we still don't fully understand is that whereas the cuprate has a good insulator on one side and a good metal on the other side, we are bounded by this weird weakly insulating upturn on both sides of the problem. And one way you could at least parameterize that is the following. If we take the normal state resistivity below or just above superconductivity, let's say, we find that the scale of that resistivity as a function of doping has this kind of a minimum. And it's interesting that the occurrence of superconducting ground state coincides where that resistivity is dipped below the scale set by a quantum resistance per nickel oxide plane. So we're just starting to get into the regime of coherent transport. Now in terms of the Hall effect, again, let me skip the details, but let me say in the broad features as a function of doping, this is a slice in temperature, and this is a more broad picture. It's qualitatively consistent with what you might expect from a two-band picture. We don't have enough parameterization to really extract the details like effective masses and mobilities of the channels, but certainly it is consistent with this notion of having two components. I should say that this is now work from a group in Singapore. And so this was the first study from a different group, and by now there's quite a number of groups in this game. And it seems like it's fairly agnostic to growth technique. So by MBE or PLD doesn't seem to matter, for example. Although it should be said that this has been in the regime of thin films and no bulk reports yet have been reported for superconductivity. So another question that arises in thinking about this comparison is whether or not you have magnetism or magnetic fluctuations relevant. And there's very little known about this. This has not been well studied. The starting point is for bulk powder compacts of the parent lanthanum nickel O2 or neodymium nickel O2. There's at least no evidence for static long-range magnetic order in powder neutron diffraction. This is Matt Rosinski's group at Liverpool. Okay. Now, the question would be, this notion of having proximate magnetism is so important for superconductivity, not just in the cuprates, but in heavy fermion and other systems. We're very curious to know what might be going on for the nickelates. The problem, as I told you, is we can only be stable up to like 150 angstroms, right? So this is miserably impossible to do by things like inelastic neutron scattering. But we've been very fortunate to collaborate with people and developments in the field of resonant elastic X-ray scattering. So a photon in and out technique, by tuning to core resonances, you can pick up, and what we'll worry about here is the magnetic excitation spectrum, despite being so thin. So this is what we found. So this is the parent neodymium nickel O2, and you can see the intensity distribution in high symmetry directions of what looks basically like what you would expect for spin waves in an antiferromagnetic square lattice. So this is quite interesting and in some sense surprising. It's quite a large energy scale, going up to about 200 MeV. Right? So if you take that data and just parameterize this by a simple near neighbor and next nearest neighbor spin model, you can pull out kind of the exchange interactions that are, for comparison, what you might find in the cuprates. So the overall statement is that you have a pretty large magnetic excitation spectrum bandwidth that is kind of order, 50 to 70% of that in the undoped cuprates as a scale. Here's some representative examples. A second feature observed in this experiment was that whereas this is also Rick's data for the cuprates, that these were resolution limited experiments, whereas in our case there's notable damping above our resolution limit by this dotted line. So this is something like the half width of half maximum of these peaks. And so clearly there's quite a bit of damping. It looks more like a doped cuprate, and we suspect qualitatively it might arise from some of these, this additional electronic channel. So let me tell you a little bit about recent things that we and others have done. So we've been excited to pursue, in more general terms, whether there's a dome of superconductivity. This is a series of samples and studies by Motoki Osada and our group, looking at the original neodymium versus praseodymium and lanthanum. Okay. And one of the motivating features was, given this initial finding here, there was lots of questions whether the 4F electrons were in some sense essential to superconductivity. It appears to be not the case, and we can collapse kind of all our data. Here it's parameterized in terms of the c-axis lattice parameter. So Bob, to your question, this is unconstrained, but the in-plane is constrained to the substrate. That's common in all of these studies. And so we suspect we're dominated by size and hybridization effects. Now, a recent surprise that has got us pretty excited is that we find superconductivity even in the parent compound, in the case of lanthanum nickel O2, with increasing crystallinity. And so just to go back here, if your eyes were careful, you might have noticed this little glitch over here and here. It does seem to be real. So this is the phase diagram in lanthanum strontium nickelate. And if I go back to the scale of the residual resistivity in the normal state, we've now dipped down below this kind of resistance scale that I described to you earlier, such that the resistivity of this guy is asymptoting to 0. We don't often get all the way to 0, but let's say 90% there by 100 millikelvin or so. Okay. So we think this is rather interesting and certainly worth more materials and measurement investigation. Some of the things we're thinking about is that this guy is, as we have been discussing, apparently self-doped, and that this might be what we're seeing. And it seems suggestive that we might be able to access a rather clean system, meaning in the absence of solid solution type of disorder, a rather interesting soup. I took this from a local theory paper, kind of illustrates the ingredients, right? You have the nickel-nickel lattice, the antiferromagnetic fluctuations that I just showed you, but also cross-coupling in this other channel to the rare earth 5D band, for example, right? Now, let me go back a little bit and tell you about what means cleaner and where are we at on that problem. So I had showed you that in the early days of the originally studied neodymium type of nickelates, we were able to make, well, we were quite proud, this was quite hard work, nominally single crystal thin films, but there were quite a high density of extended defects. Without going into the details, these were often, let's say, antiphase boundary shifts or so-called Ruddleston-Popper intergrowths. And we got better and better at eliminating them, but they're still there to fairly high density. Okay? So our question that we don't know the answer to is, to what degree is scattering dominated by these extended defects or that associated with the solid solution disorder? What's interesting that when we go to a larger lanthanum nickelate, it's slightly more comfortable on our substrate, and we can largely eliminate these sorts of extended defects. We actually find a different one, right? I don't know if your eyes can see these little diagonal slants here, and if you look at this in terms of a relative rotation or the ratio of the in and out of plane lattice parameters, the simple story is this is like the guy wanting to go from planes in this direction, rotating up and back down, okay? And so this is kind of the dance in our lab, right? That we've gotten rid of some defects, we're near the instability to other ones, and the question is, can we really eliminate this? I think we're very close now to get towards what we would call the intrinsic kind of behavior. And so again, a speculative view graph, but what's exciting us is that if that self-dope picture is correct, if I think about some sort of cartoon landscape of a correlation strength, a doping, and disorder scale, that the slice we're taking with the nickelates is a little bit different from in the cuprates. Namely that we're off of half filling by the self-doping, and we're taking certain trajectories in this space. And I want to compare that with what we might think we're doing in the cuprates, the 214 cuprates. And so this is both an old and new story. So it was already long understood that this cation disorder and the size disorder was important. This is an early paper by Jan Atfield that showed that what he basically did was the following. He took a 214 cuprate and mixed all sorts of different things such that the overall doping level was the same, but the variance in the A site cations was varying, and you could see that TC was linearly related approximately with this variance. And more than 20 years later, this still is bearing fruit. So I think some of us heard recently Bernhard Keimer talking about their recent work, where their logic was that by going to lanthanum calcium, right, that is nominally closer in size in terms of their formal or approximate ionic radius, has a different degree or lower degree of disorder, and compared to the original 214 cuprate dome, let's say with lanthanum strontium, that this seems to extend quite a bit higher, and attributing that to reduced disorder. So again, it's speculative, but we're pretty interested in studying this aspect and using the fact that we can vary, the lanthanide series and hopefully change essentially different discrete points on this axis in the absence of solid solution disorder. So this is one of the things that we're pushing on next. So finally, I never told you why I called this an infinite layer nickelate if you're not in the field. And the reason is that if you look at the chemistry of this family, it's quite interesting. Let's just focus here. I've told you about so-called infinite layer nickelates, meaning all the stacks are right one up against each other. But it's part of a homologous series where you can have one layer, 2 layers, 3 layers, and so forth, spaced by a rock salt layer. So it's infinite in the sense that it's the n equals infinity limit of this family of compounds. Okay. And so this was, I think, first reported in 1992, right? That you could make or think about making these sorts of compounds. And one could imagine that there might be the possibility of an extended family of superconductors along the structural motifs of the cuprates and the nicktides and many systems that we know and love. And very recently, the first steps indicating that's the case have been reported online. So this is a reproduction of a cuprate phase diagram. And the interesting point of this layered, in this case, 5-layer structure, is that this spacing layer is essentially doping this guy, such that the average doping level or whole doping level of this is 1 over n, where here n is equal to 5. In fact, this thinking has already been around. This was work from Argonne National Labs, where they had studied in detail the n equals 3 or a tri-layer phase. And what they found was, depending on the composition, either a metallic or a density wave insulator ground state. And they speculated that maybe they have kind of gone too far in doping. But actually, then if you go to n equals 5, you would live nominally in the superconducting dome. And first reports seem to indicate that indeed these 5-layer compositions are superconducting. So I think I've gone at or past time, so let me just conclude there and simply thank you for the opportunity to show you a little bit about recent work on layered nickelates. It seems to be an interesting new family of superconductors with aspects that are reminiscent of cuprate and intermetallic physics. One of the key qualitative distinctions is this so-called charge reservoir layer in the language of the cuprate seems to be actively hybridized, and that leads to rather distinct electronic structure and doping evolution. And so this is very much at the early stages, many open questions, lots of theory work on this, I should say, but experimentally, can we address the pairing symmetry? What are the scales of achievable TC? And as I told you, I'm rather intrigued about the nature of this undoped phase. So let me close there. Thank you for your time, and I'm happy to take any questions. Please.
Can I start, please? Could you please go back to the slide with the magnetism on it? The high, yeah. Now, this went by awfully fast. Is this a superconducting sample?
This sample is not.
So what is this sample?
This sample, let me see, specifically would be the undoped neodymium nickel O2. Here's what the resistivity looks like. Like I say, it's weakly going up. All right. I can maybe.
I could. And then this was done how? Neutrons?
No, this is by using resonant inelastic X-ray scattering. So going on the nickel L edge, right?
That's right. That's right. So.